Okay, thank you for listening and being part of this video. So you'll know probably by now that this video is intended to cover some of the work that you've studied before in Year 11 Math Methods, in a hope that you can run through a lot of this yourself. But obviously, if you have questions, you must ask them and make sure that you're comfortable with the work. So this is the exponential functions, a little bit of work on Euler's number, some index laws review. It's exercise 6A, 6B and 6C, as you can see there, and I'll probably split this video up into a couple. You'll notice there's some learning goals, success criteria. This is all on the OneNote, so refer to this if you need to. So let's move on and have a look. The first thing I'm going to talk about is sketching exponential functions. And this follows the same properties as all of our work on sketching functions, so nothing really changes here, but I will run through this again. You'll note, first of all, that we're dealing with y equals 2 to the x. This is chapter 6. We've already done some work on chapter 8. So you'll already have been introduced to the number e, which I'm going to reintroduce later on in this video. To start with, we're working on the assumption that you don't know e, and we're sketching y equals 2 to the power of x. So here is a sketch of y equals 2 to the power of x. At 0, this point here, when x is 0, y is 1, because 2 to the power of anything equals 1. 2 to the power of z equals 1. And when x is 1, y is 2. 2 to the power of 1 is 2, so on and so forth. It's not a perfectly accurate graph, but that's the point is made there. This has an asymptote at y equals 0. This is a horizontal asymptote. It does not have a vertical asymptote. It looks a little bit like it's got a vertical asymptote, but it doesn't. And to think about this, consider this. If I pick a really large number of x, say up here, 1,000,000, well, does y still exist? Yes, it does. It's just really, really massive. So it does continue on. This little purple line here continues on forever, but it just takes a long time to get there. So there is a vertical answer, or a complete domain, but there is a horizontal asymptote. X cannot go below, so y cannot go below 0. That asymptote will move based on some of our variations with our transformations. So let's have a look at some transformations now. The first one we've often dealt with is the A transformation, which is a multiplier on the outside of the function, so it affects the vertical components. It's on the outside, which kind of means it's closely linked to the y as opposed to the x, and the y obviously is our vertical. So it's called a vertical dilation, or a vertical stretch perhaps, and it operates like this. A does exactly what you'd expect. If A is 2, it stretches away from the x-axis by a factor of 2. So I've got two examples here. I'll do the first one in green. 3 times 2 to the x will take each term and stretch it away by 3, or dilate it away by 3. So this was a gap of 1, now it's a gap of 3, and so it's up to there. This was a gap 1, 2, now it's 1, 6, it's up to there. And you'll see that we get this very similar shape, but now it's a lot steeper. It's been stretched or dragged away from the x-axis. And I'll do the second one in light blue. So that's y equals -1/2 2 to the power of x. Now this negative flips the function over the x-axis. It takes every result, or y value, and it makes it negative. So that means that every single term we had before, let's say this one here, will now be there. Except we've also got a stretch of 1/2. So that's a compression towards the x-axis, which means we're now there. This 1, 2 will become 1, -1. It's been flipped and it's been compressed, and so it will look like this. It's just squashed up to the x-axis more, and it will go out like that. Same function, squashed and flipped over the x-axis. That's what the A value does. Now let's talk about the B value. So we've got y equals 2b to the power of x. Now, you may have heard us talk about this before, but just keep in mind that for y equals 2 to the power of b, I said 2b to the power of x, sorry, 2 to the power of bx, this can be written as 2 to the power of b to the power of x, and then we can change that 2 to the power of b to be something else, let's say capital B. It becomes capital B to the power of x. Little b is just a constant. So if we did 2 to the power of that constant, then obviously this is changing the base as well. So the b actually can be incorporated into the base. If we're definitely using base 2, well then the b is important. But if we're using any base, we don't really care, well then we don't really need a b value. So there's some little variations there. B is on the inside of the function, so here it is here, and therefore it's quite closely linked to this x rather than a y, which makes it a horizontal, and it's still a dilation. So this time we're compressing in or out from the y-axis. That's what's happening this time. Let's have a look at a couple of examples. Y equals 2 to the power of 3x. I'll do this one in orange. Now it turns out that we're actually compressing in. So if we've got 2 to the power of 3, so if b is 3, we actually squash the graph in, and by a factor of 3. So 0, 1 stays as 0, 1, but 1, 2 becomes a third, 2. And just imagine for a second the reason why this is. Y equals 2 to the power of 3 times a third is now 2 to the power of 1. That's why a third is now what 1 was. And of course this means that we've got that compression hole out. So we get something that looks like, I'll just take this point here, there's 3, that's there. It will look like this, and it will go under, but it still won't cross, it'll still asymptote with that x-axis. So it's just steeper, and it will still cross at the same point, 0, 1. Y equals 2 to the power of negative x on the other hand, which I'll do in green. Well, this is, that negative is a reflection again, but this time it's a reflection over the y-axis, because it's making each negative x value negative, and then translating that, so it's a reflection over the y-axis, exactly the same function as the purple function, but reflected over the y-axis. So it now looks like that. As close as I could do to get in it accurate. But hopefully you get the point. The negative there will provide a reflection. Okay, so there's our b value and our horizontal dilations. Let's have a look at our next one, and these ones are actually a bit easier. So our c value here, and we write it as negative c, which I'll explain in a second. This is quite closely linked to the x, and therefore it's a horizontal, and because it's added or subtracted, it's a translation. But on the inside, when we've got something closely linked to the x, it actually works opposite to what we expect. So we typically write x minus c in our transformations, and that will then shift in a positive direction for what the value of c is. So if c was 2, it would move 2 this way, and if c was negative 3, it would move 3 that way. And we've got an example here, y equals 2 to the power of x minus 2, and so it is, now c is 2, which means the whole thing just shifts 2. That moves 2 there, this one moves 2 to there, and each of these points, this point here moves 2 to there, and so on and so forth. I mean, the same function, but shifted. Now, the horizontal gap should be 2, that gap there, the whole way. It looks like it's really close in here and really far away over here, but actually we don't care about the vertical gap, it's the horizontal gap that should be 2, so it will look like it gets closer as it gets shallower, so not as steep. But there we go, that's a horizontal translation, works quite nice and easily. And then last we have our vertical translation, and I've circled here or rectangled here and noted that this is the asymptote as well. So our plus d is more closely linked to the y, and therefore it's a vertical translation. It's on the outside of that special function here. It's just being added onto the end. The vertical, it's a translation, plus d just shifts it. If d is 3, it shifts it up 3. If d is negative 7, it goes down 7. And we've got the example 2x plus 3, and so I'm going to shift it. I'll do this one in red, and I'm going to shift everything up 3. So there's the first one, it goes to here, this one goes to here, etc., etc. And our asymptote actually also shifts up 3. This is the only one that can affect our asymptote, unless we have a translation and then a vertical dilation. That could move the asymptote a bit as well. But for now, we have just a translation, and that's the only one in its original form will affect the asymptote, and it'll look like that. That's pretty poorly drawn, but it should be that purple graph just moved up. So any of you who do art, I apologise. So there we have our different transformations, and transformations is a big grouping word for translations and dilations and reflections, and you can see where they all come from. We do have, obviously I talked briefly about this base, so we can change the base, and I'll just take you through that quickly now because it will be important when we start exploring E. So if we have y equals 2 to the power of x, and we want to write it base 3, well, we need to ask ourselves, 2 equals 3 to the power of what? That's our question. And of course, to be algebraic and mathematical, we might change that what to be x. And then we will rearrange this. So that means that x is equal to, so that's incorrect, log base 3 of 2. So that's our rearrangement into a log form. And so we get this. Y is equal to 3 to the power of x, which is 3 to the power of log base 3 of 2 to the power of x. And probably I shouldn't have used x here. I might just take that back and change it to a y, just purely because I've already got x there. Actually, I've already got y. What am I doing? Let's change it to an a. Oh, that's one of my dilations. I'm really messing this up. M. There we go. So we've got that change of base rearrangement, and that works quite nicely. You don't have to worry too much about this. Basically, it's just a number. Log base 3 of 2, very quickly on a calculator, is 0.631 is log base 3 of 2. So you just get some constant there. So you can change your base, which is really important. And y equals 2 to the power of x can be changed to y equals 2 to the power of 0.63x. On the other hand, if you just wanted to draw y equals 2 to the power of x, what happens when we have a different base? Well, obviously 3 to the power of x is just actually going to be larger numbers. The y values will be larger numbers. So we'll still have this 0, 1. I'm doing this one in pink now. So I'll denote there. We still have 0, 1, but 1, 3 to the power of 1 equals 3. So that goes there. And 3 to the power of 2 now equals 9 instead of 4. So it's right up there. It gets very steep, very quick. And there it is. And this is interesting because we get y equals 2 to the power of x is y equals 3 to the power of 0.631x. Whereas in here, we've got a 1. So we've actually had a b value change from 0.631 to 1, which is a dilation. And you can see the dilation's happened there, it's stretched it out. So actually, it makes perfect sense what's happening because it's just a vertical dilation. Sorry, a horizontal dilation, so it's a compression, which is what we've got then. Okay, so that's actually the end of the first exercise with the exception of this one example. So I'm going to run through now how to sketch a function, base 3, that's got these different dilations. And just to give you a bit of an idea, but I would like to just point out, and to do this, I might just quickly take a copy of this graph here, and I might just draw a couple of things. So obviously, I'm going to take you through a bit of a stepped out process, and we really want you to understand the stepped out process. But when it comes to sketching a function like this, particularly in the exam, the main things are that you've got the key points. And the key points are going to be the X and Y intercepts and the asymptote. So when I look here, I can see that this function has an asymptote at -2. So it's down here. So I'll just draw my little asymptote here. -2, I might even write asymptote in an exam. And it's a base 3 function, but it's also got some translations in there, so it's been shifted around. So I've got to be a little careful, but I do know that it's going to run through above that. It's not being reflected over the x-axis. It has been reflected over the y-axis, you can see there, which means it's going to look something like this. Now, what I want to know is what is the x and y intercepts. So one way you could do this is to first work out the x-intercept, and it's really important to recognise that's when y equals 0. And so we get 0 equals 3 to the power of -2x plus 1 minus 2, which means 2 equals 3 to the power of -2x plus 1, which means that -2x plus 1 equals log base 3 of 2, and that means that x is equal to log base 3 of 2 minus 1 over -2. And so putting that quickly into a calculator, I get x is equal to -0.185. And so I can actually plot that on there. -0.185 is my x-intercept. And then my y-intercept, which I'll do in a different colour again, purple, y-intercept occurs when x equals 0. This one's actually a bit easy. Usually the y-intercept's a little bit easier in most functions. And so I get y is equal to 3 times -2 times 0 plus 1 minus 2, and that is equal to 3 to the power of 1 minus 2, which is just 3, minus 2, which is just 1. And so the y-intercept is 1. And it's at this point that I recognise I've made a minor error, and that is that actually this should be positive. So my apologies. If you're following along in the calculator, you will have noticed that. So that's incorrect, and it should be here. And of course, in orange now, I can see that my function looks something like that. And it's got the important points, so I would mark here that that is 0, 1, and I would mark here that this is 0.18, 0, and in my important points I've got my asymptote label. Over here though, I might do the same thing again, but I'm going to start by tracking in different colours each step along the way. So let's start with 0, 1, 1, 3. This is y equals 3 to the power of x. So I'll put these on here, 3 to the power of x, and then in red I'm going to draw y equals 3 to the power of negative 2x. So I'm just slowly doing it first, and I usually like to start with my dilations. So that negative 2 is going to do the reflection over the y-axis, and then the 2 on the inside is going to compress. So I'll get this point here will reflect over and go compress to halfway. This point stays where it is, so I get something that's a lot steeper and reflected over the y-axis. Okay, that's all good and well. And so next in 2, I'm going to do my +1. And you'll notice here that the form's slightly different. We've got to be careful here. So this is a nice point to make. If you start with y equals 3 to the power of negative 2x, there's our b value. And we want to go to y equals 3 to the power of negative 2x plus 1. We actually have to factorise the b out. The c transformation will be based on being multiplied by b. So I'm going to factorise it out as negative 2x and then minus a half. And you notice here if I expand that, negative 2 times negative a half will give me that +1, but it actually creates a translation by plus a half. So everything moves plus a half. So I end up with this point here, which is actually 0, 3, interesting enough, and that point moves out by a half, and I get a function that looks like this. It hasn't moved much, but it looks, and I've not done a great job here, but basically it's just shifted by a half that way. And so it's y equals 3, and I'll go back to the original form, 2x plus 1, but we do need to consider that factorisation because the c has to be have a b value included for it to actually be a translation. So last of all, we've got the -2 on the outside, which I'll do in orange. Everything's shifted down 2, so this of course goes to there, this goes to there, and I've now got my other factor there, and I'm not sure how this associates to the red, but it will go down like this. Okay, and you can see my key points there and there are the same as my key points over here, and I've got the same asymptote. There's a couple of ways you can go about it, and to be really honest, this is probably your best bet, but a good understanding of transformations can really help you make sure you're in the right place, and you might be asked to describe the transformations that take place between two graphs, so it's important to know.